And now it's the time to move to the second speaker in this session, with Professor Gerard Fernando, the Chair of Polymer Engineering in 2005 at the School of Metallurgy and Materials, so the University of Birmingham in United Kingdom. He will give us a talk on chemical process monitoring and structural integrity assessment using optical fiber sensors.
Hi, ladies and gentlemen. I'm Professor Gerard Fernando, and the title of my talk is Chemical Process Monitoring and Structural Integrity Assessment of Composites Using Optical Fiber Sensors. I'd like to pay tribute to all the people mentioned here who have made a contribution in some way or form towards this presentation. So thank you all very much indeed. There are three issues that I'm going to focus on for this presentation. The first one is the chemical integrity or reactivity of resin systems apparently does not change over its shelf life. So for example, if you buy a pre-preg, it's given a shelf life of 18 months if it's stored at -18 degrees Celsius. The processing schedule does not change over those 18 months, meaning that the chemical reactivity hasn't changed. So that needs to be looked at. Secondly, the integration of optical fibers into fiber-reinforced composite preforms can cause a distortion to the reinforcing fibers, and this can be detrimental in some applications. And thirdly, when it comes to structural integrity monitoring or assessment of engineering materials and structures, the hypothesis is that you really do need to have access to more than one measurand to have a comprehensive assessment of the structure of that material, be it chemical properties, the mechanical properties, thermal properties, optical properties, etc. So these are the three key things that I will talk about. The approach that we've taken is, first of all, we've designed and used a large number of optical fiber sensors for monitoring cross-linking reactions because we're interested in thermosetting resins, or this is known as the cross-linking process or curing process. We've also then said to overcome the problem associated with the spatial distortion of the orientation of the reinforcing fibers being perturbed by the introduction of optical fibers. We've looked at using reinforcing glass fibers, EClass, S-class, and so on, as the optical fiber or sensor. And thirdly, we've deployed multi-measurand sensor systems, meaning you can get more than one type of measurement. It could be refractive index, strain, temperature, pressure, vibration, or acoustic emission. I'll be talking about a lot of these parameters, and if you're interested in using optical fibers for acoustic emission monitoring, then please have a look at this reference here. So I think we'll start with saying, what is an optical fiber? It consists of a core and a cladding. This can be a continuous silica rod, and it's surrounded by silica cladding. The diameter of an optical fiber is a telecom's optical fiber is 125 micrometers. The core diameter varies. If it's single mode, it's pretty small, it's between 6 and 10 micrometers. And that means this single mode fiber can only propagate one predominant mode of light down the core. And in multi-mode fibers, the core is significantly larger, and therefore it can sustain a larger number of modes in the core. The overall diameter is 250 micrometers, and that includes the buffer or protective coating that is used over the cladding. This generally tends to be a polymeric coating. It can be an acrylate, polyimide, or silicone. I'll be making reference to a refractive index, and I thought I better define it. It is the speed of light in a vacuum divided by the speed of light in the medium that we are interested in. In the case of our optical fiber, a prerequisite is that the refractive index of the core must be higher than that of the cladding. So let's have a very quick textbook look at how light propagates within an optical fiber and the conditions required for it. There are just two key parameters I will focus on for today. I have here material A with a refractive index NA and material B with a refractive index NB. And the index of A, refractive index of A, is much higher than that of B. So there are two conditions here. First of all, I'm launching light, monochromatic light. A ray of light is being launched at 90 degrees to this interface. So I launch my light, and according to Snell's law, some of the light at this interface will be reflected back, and the rest of it's transmitted. I then increase the angle of incidence, θ1, and you can see the ray of light now is partially refracted and some of it's reflected. And I keep increasing the incident angle from θ1 to θ2, and the refracted angle also increases in tandem, and you still have your reflected, partly reflected ray of light. At a specific angle, known as a critical angle, the bulk of the light now travels along the interface between material A and material B. And so this is known as a critical angle, and you still have your partially reflected critical ray. At angles greater than the critical angle, you have total internal reflection. So the two phenomena I'm going to be using are what happens at this interface when you have total internal reflection, and what happens when you launch light at 90 degrees to the interface between material A and B. And we will refer to this particular case as reflections at normal incidence. I want to now convert the diagram you saw earlier into an optical fiber. So I've done it like this. So this is my core and my cladding. So this is my core in yellow. And this here is a cleave or a section or a cut at 90 degrees to the long axis of this fiber. That is important. So I'm launching my ray of light into my core. It comes in. So let's just imagine this is now floating in air. So this is all air. The light is launched in. Now at this interface, so this is the silica interface, and this is air now. Some of the light is reflected back down the optical fiber, and the rest of it's transmitted until it hits another interface. So how do we actually utilize this principle for monitoring cross-linking reactions? There is a simple equation, and this is known as the Brunel reflection coefficient, R, and that is given by this simple equation here. So N core is the refractive index of the core, and N air, because I said this was floating in air, can be the refractive index of A, which you normally assume to be 1, or it can be a medium that is surrounding this cleaved optical fiber. So this could be your resin system, or it could be a bucket of resin, your pre-preg, your filament winding machine, or your pultrusion line. And by using this equation, this takes a parabolic form. If the refractive index around here is changing, by monitoring the amount of light that's reflected back down here, because that is influenced by the refractive index of the medium here, you'll be able to infer as to what's happening in terms of the refractive index changing here. If you're interested in looking at the basic equations, please have a look at this reference here. So we'll have a quick look now at typical epoxy resins, and I've given you the nomenclature as to where all these different terms come from. There are a whole wide range of resin systems that you can buy on the market, and your high-performance aerospace resins generally tend to have this multifunctional epoxy group. So this is your epoxy group. You can see there are 4 epoxy functionalities that can take part in a reaction that we will see shortly. You also need to activate the epoxy group, and you have a range of hardness or curing agents that you can select from. They also have a wide range of applications and very different classes of resins, hardness, depending on the reactivity that you want and the end product that you want. So how does this now relate to what we're after, developing a simple sensor system? I've just picked this type of hardener and this resin I mentioned previously. It becomes very tedious to write out generalized reactions involving the whole lot of these species. So I've taken the short form. I'm calling the amine group, and I've color-coded it as such. So this is the NH2 group. So the rest of this molecule here is represented by R prime. I've done the same with my epoxy group. And so now we need to mix this thing to components thoroughly, degas it, and activate it, for example, by applying heat. And this is what happens now. When you provide energy to the system, this hydrogen here will react with this reactive oxygen on the epoxy molecule to give you a covalent bond between the nitrogen and the carbon. So you're forming a covalent bond between the nitrogen and the carbon with the formation of a new functional group that is a hydroxy group. Now this hydrogen, the secondary hydrogen, amine, is still reactive. It can react with another epoxy molecule, and then you have your normal covalent bond between the carbon and the nitrogen and the formation of a new hydroxyl group. So I hope you can imagine, because you have these tetrafunctional epoxies and you have 4 hydrogens that can react on each one of these species, in your resin system, this reaction will lead to a highly cross-linked structure. And if you were to monitor this reaction spectrally, you'll see the concentration of this and this decreasing and the hydroxyl increasing. The molecular weight increases as you are joining all these small components together to form your highly cross-linked structure, which cannot be dissolved in any solvent. There's a problem with recycling, obviously. The molecular weight increases, the optical density increases, and therefore the refractive index throughout this reaction process will also increase. These are exothermic reactions, and therefore they'll liberate heat, and you need to monitor the heat. There is also shrinkage because you're joining two smaller species and making larger species together. So there are a number of parameters that we can monitor: the strain, the temperature, or the refractive index, or infer the refractive index using optical fibers. And that's what I will aim to show you now. So this is my cleaved optical fiber. We said this is the equation that dictates how much light is reflected as a function of what is surrounding the cleaved optical fiber. This equation is only valid for fibers that have been cleaved at 90 degrees. If you don't cleave it at 90 degrees, the equation becomes far more complex. So this is my cleaved optical fiber now, with a resin system around it. And though, as we said, because the refractive index changes as you cross-link this amine and epoxy group, you can actually track the progression of this reaction. And this is a cheap and simple way to track cross-linking reactions in your prepregs, in an autoclave, in a filament winding line, etc. But do remember, this is an intensity-based sensor. You're measuring the intensity of the light, and also it'll be influenced by temperature. But the instrumentation is relatively straightforward and cheap. You have a light source, you connect that to an optical fiber. This is a coupler that splits the light. I'm happy to explain this later if you wish. You're putting in one optical fiber into it, and two come out at the other end, and one is also the return part. So this is called a fiber optic coupler. It splits light, the standard telecoms component. The light comes in, you put it in one arm into an index matched gel, and that's because if the refractive index of the core is the same as the gel, then you get no reflections coming down here. On the other hand, this second arm here is put into your reaction vessel or your prepreg, and then you measure the reflected light intensity at your detector as the reaction proceeds. This is such a simple system, 125 micrometers in diameter. You can insert them wherever you like. We've chosen to put them into differential scanning calorimeter, as the picture here shows you. We've also inserted them into rheometers and other items of equipment. And what you're looking at here, if you look at the red trace, as you heat up the resin to initiate the cross-linking reaction, the refractive index will drop, and then cross-linking takes over at some stage, and the refractive index will increase. The blue trace is what you will get from a typical differential scanning calorimeter. That's what DSC stands for. And by computing the area under here, you can infer the reaction constants and the rate of reactions for this particular resin system that's been cured isothermally. If you are interested to hear more about this, I've given you a reference here. Now, the good thing about optical fibers is you can use them for process monitoring, but then after you do the process monitoring, you can also use them for monitoring the integrity of the material. Here, the same sensor I showed you previously has been subjected to a second scan in the differential scanning calorimeter. The red trace is showing you that you can indeed monitor the glass transition temperature by looking at the magnitude of the Fresnel reflection. I think this is the first time this has ever been done within the confines of a differential scanning calorimeter. And this is a typical change in heat capacity trace that you get from a differential scanning calorimeter, where we take the midpoint as the glass transition temperature. So it's a very cheap and cheerful technique to study moisture ingress, glass transition temperatures, and anything else that will change the thermomechanical properties of resins and composites. So the second part of my issue, I said about the spatial distortion caused by the embedment of large diameter optical fibers, 125 micrometers in diameter. EClass Fibers for 2400 tex, it's about between 24 and about 18, depending on which supplier you use. And we've also have access to custom-made optical fibers, which are about 23 micrometers. You can see that this is a significant increase in the diameter when compared to reinforcing fibers. And there are consequences when you embed optical fibers in prepregs. You can get a resin-rich region, but also notice here, even if it's a unidirectional composite preform that you're embedding your optical fibers in, the layers below can be distorted because of this relatively large diameter. So the solution for this, or one of the solutions for this, is to use the glass fibers itself. If you took this and you potted and polished it, this is what half a glass fiber bundle will look like. These are individual filaments of EClass. You can put connectors onto it, and then now you can actually start to study reactions or damage that happens when you manufacture your composite, because you can guide light into conventional glass fibers. And here we've looked at chemical reactions, and then we subsequently manufactured literally void-free composites and tabbed them, tensile tested them whilst monitoring the light intensity going through each one of these filaments. It's relatively easy if you have good quality fibers, reinforcing fibers, where the binder content is pretty uniform and low. But depending on where you get your fibers from, you can also have pretty bad binder distribution, which does mess up the measurements. So how do you actually use optical fiber sensing technology with EClass fibers, for example, to monitor chemical reactions? This is a diagram similar to the ones that we spoke about before, where the light is propagating by total internal reflection within the core of the optical fiber. Every time you have total internal reflection, so the refractive index of N1 being higher than that of N2, at this interface between the incident beam and the reflected beam, there is a standing wave that is set up at this interface. And the intensity, the electric field intensity at this interface decays exponentially into the cladding. So the intensity decreases very rapidly as you leave the cladding. So this is why I hesitated when I said light propagates in optical fiber total internal reflection. That is true. The majority of the light is contained in the core, but there is a standing wave that's propagating along the cladding. That wave is known as the evanescent wave, and the field associated with this is known as the evanescent field. And I'm showing that here in a magnified version to show you this is the evanescent field that is present at the interface anytime you have total internal reflection. Therefore, if you can access this, the evanescent field, and if you put an absorbing material like your amine or your epoxy, that component will be absorbed. It's very similar to transmission spectroscopy. And therefore, if you can have access to this, you can actually do evanescent wave spectroscopy on the reinforcing fibers without relying on embedded sensor systems. That's what we did here. This is conventional EClass fiber, connectorized. The distance doesn't matter because the chemical reactions taking place are actually at the interface between your actual reinforcing fiber and the actual resin. Sorry for the stressing of the word actual. So you can actually then look at conversion of epoxies and amines, fit them to various models, and you can get rate constants for a particular resin system. So if the resin is aging, this behavior will deviate and you know you'll have to do something or get rid of it. We also compared it with conventional transmission infrared spectroscopy, and we get very similar results. So this is just to prove that you can actually use reinforcing glass fibers as sensors to perform spectroscopy to get reaction kinetics at the interface, as opposed to putting optical fibers in. The next topic is, there are also other sensor designs we've looked at. You can look at optical fibers with cradles. You put the resin in, and then light goes in through the resin, and then you connect this to a detector, and you get conventional spectra like this. So, but this is quite a tedious way of doing things. I'd like to move to the third item, which is looking at damage in composites. I'm not going to be spending any more time on this other than asking you to have a look at it. And the moral here is it is an extremely complex and convoluted topic when you start looking at damage initiation and propagation in fiber reinforced composites. And this is why I believe you need multiple measurements. I'm going to spend a minute explaining this multi-measurand sensor system to you. There are references available that describe it in greater detail. This part here is known as the Fabry Perez sensor. So you have optical fiber, conventional 125 micrometers in diameter, that is put into a capillary with a bore diameter of 128. The overall diameter is large, it's 300 micrometers accepted. You join the capillary to the optical fiber by fusion joints. So this is a standard telecoms kit where you can fuse the silica capillary to the silica optical fiber. We wrote a grating right at the end of the optical fiber, meaning this particular part of the grating cannot be loaded to any great significance, and therefore the grating is, I'm sure you heard about this, the fiber Bragg grating is a periodic modulation of the refractive index of the core of the optical fiber. So you have this periodic modulation in the refractive index. So in our case, since this can be stressed mechanically, any changes in temperature will change this periodicity, and therefore you can monitor the temperature here because it's not mechanically loaded as it's within the capillary housing. This part here is known as the Fabry cavity, and you can interrogate this cavity length very accurately, looking at the interference fringes that form and reflections taking place here and reflections that take place of this reflective coating. And therefore you can get very accurate measurements of strain, temperature. And then to try and get information on strain and temperature whilst you're monitoring the cross-linking reaction, we parked a number of secondary optical fibers along this primary optical fiber, creating a cavity similar to the cavity I showed you previously. So the resin goes in. This is a reflective coating on the end face of my capillary. I can do transmission reflection spectroscopy. So I think this is the first time where you can get reaction kinetics from here, strain from here, and also temperature from here. Sorry, that was the other way around. You can get strain from here and temperature from here. If you parked other optical fibers, cleaved optical fibers, well away from a reflective surface, you can also measure the refractive index like I showed you previously. Now, making all of those sensors are tedious. This is a recent publication about to come out where we use a conventional focus ion beam, which is becoming very common in materials laboratories to create Fabry cavities with very good end face cuts to act as cuvettes or to act as strain sensors and temperature sensors and refractive index sensors. So we'll be furthering this work in the near future. Because you can use conventional optical fibers as light guides, this is EClass Fiber composite. You notice if it's been impact damaged, if you introduce white light or green light, it will green light simply because EClass absorbs everything but green. You'll have bleeding light, and you can then visually detect this. All you need is a laser pointer. And you can also monitor the cross-linking reaction. So this is the first time I believe you can not only monitor the cross-linking process as to what the quality of the interface chemically is, and then you can mechanically load this or look for damage, and you can see fibers fracturing in real time. The next phase is to try and make this a coherent bundle so you know exactly where the fibers are fracturing. Reference if you're interested in that later. And I'd like to conclude now, and rather than giving you a standard conclusion to a different, I'll just highlight some of our past and current research. This is behind the Tate Modern in London, where this is a 49-meter rebar cage that we instrumented to monitor the strain as this foundation was put in place and 14 stories were built above it. This is the Westmill Bridge in Swindon, England. This is Europe's first all-composite road bridge. We embedded sensors in here to monitor strain and temperature, and also to get the vibration signatures from this bridge so that we can tell the class of vehicle that is actually going over it or person running on it. This is a project that just finished last month where we are fatigue testing at a different institute. This dark structure that you can see here is the world's first all-composite railway bogie. So this is the platform that carries the carriage on top. And this is made out of a mixture of virgin carbon fiber and recycled carbon fiber. I can't show you the actual structure, but it's built in two halves. This is what this bogie looks like. What I just wanted to show you here is the complex route that we have to take to measure strains in different directions and also temperature. There is an equivalent top half to this, bottom half to this, which I'm not showing, with an equally complex route and arrangement of fiber optic sensors. And the good thing I found about this was done at Huddersfield, the fatigue testing. when we were logging and controlling the equipment for data acquisition from our sensors at Birmingham. So this is how far the technology has moved on since I first started in optical fibers in the 1990s. A quick look at some of the real-time data. This is not a simple fatigue test. It's got a multi-axial loading, and you can also display the data in different ways for monitoring. And finally, we've developed techniques for environmentally friendly pultrusion and also clean filament winding. This slide may be of interest to some of you, where we've developed the technology for spreading reinforcing fibers to give you a near monolayer. So you start with a width of about 1 or 2 millimeters, and then we can spread it to give this near monolayer fibers. It's very good for studying hybrid composites, and that's what we hope to do. Our latest development here is the so-called vertically aligned or Z-axis composite. So this is a skin, and this is replacing the conventional core of a sandwich, and then there is a skin on top. So what you're looking at here are vertically aligned short EClass fibers. And I would just like to point out to you, if you look at the blue histograms, this is aluminium conventional honeycomb sandwich, Nomex honeycomb, and you're looking at lateral compression, and we beat this by orders of magnitude. Each one of these vertically aligned fibers acts like a composite pillar. If you're interested in that Z-axis composite, this reference here and the fiber spreading is given in here. And I'd just like to finish off my talk with 2 issues which I think we do need to pay attention to. And the first one is recycling. Being it thermosetting material, it is awfully difficult to recycle them. So what I'm trying to show you here is there's a lot of work going around the world looking at end of spool utilization, making recycled fibers into preforms, but very difficult to achieve the properties and the orientation, the fiber volume fraction at commercial rates. This is our attempt at looking at electrostatic deposition of short fibers bundles of carbon. We can get about 80% orientation at a commercial rate, but again, it is very difficult to get uniform coverage, not because the technique is bad, because the fibers are not uniform or the bundles are not uniform. And finally, polyacrylonitrile is the primary precursor for the production of carbon fibers, and we need to find alternative precursors to produce carbon fibers. What you're looking at here is our latest innovation in electro-spinning. You're looking at nanofibers. These quasi-isotropic fibers were not laminated. This was actually fabricated by rotating the electrospinner head itself. So what I'm trying to imply here is we can apply this technology from polyacrylonitrile, which is what these fibers are, to lignin, which is derived from biomass, which we are working on currently. I'd like to acknowledge my funding bodies and all the people who have contributed to this presentation, and I would like to dedicate this presentation to the memory of Professor Brian Ralph. So thank you very much indeed for your attention. I hope you've enjoyed it. Thank you.
Yeah, thank you very much, Professor, for a very interesting presentation. I noticed you already addressed some question in Q&A. Thank you for this. We have time for one question. Yeah, Dr. Nikhil, you have a mic now to ask.
Yeah, thank you. Thank you very much. Thank you, Professor Fernando, for this lovely talk. Took back a lot of memory in my mind, especially in bridges. I had posted a question. So as we look at the inorganic oxide composition of glasses, I think you touched on this with the glass refracting everything but green light, for example. But as we move to, say, S2 glass or some of the newer glasses coming out of Owens Corning, like the H² glass, 100 megapascal, they're changing a lot on the oxide composition. What would that take? Would that take just recalibrating the unit every time you bring in a new glass, or do you have to restudy the whole system? Are there more complexities, let's say, of using that as the actual sensor itself?
I think there will be some calibration experiments that will be required, but if you want to look at, if I can split my answer into 2 different components, if you're interested in the treatment of the glass fibers with the silanes, that can be done because you can actually pick up the siloxane bond on the surface of the glass fiber. That shouldn't really change, but then the thing that would actually influence it is what sort of binder are they putting on it and how uniform is it? And that is always the stumbling block when you look at commercial systems, but there is no technical reason as to why you need to do an elaborate study. Provided you can get the light in, you can actually do evanescent spectroscopy to study the interface reaction between your silane and your thermoset or thermoplastic material. And the damage is, again, twofold answer. You can, depending on the transmissibility of the light in the through thickness direction, you can actually raster scan the surface, provided you can get the light in. You can see as you approach damaged fibers, they'll actually start glowing depending on the oxides that are in there. And we need to now, I think, move from what we've demonstrated to actually developing a coherent bundle, so you know where the fibers are fracturing and which neighboring fiber is going to fracture. And then on top of that, if we can actually get to the innovation where we can write some sensor or put a sensor in, not only can you measure the strain transfer, you can also study the sequential failure sequences, which I think are of great interest to me personally.
Sure. Thank you. Thank you.
Yep. Okay. Thank you. We still have one question in Q&A. So if you can just address this question by typing, because we have to move to the next speaker now. So thank you, Professor Gerard, for this interesting talk, and we enjoyed the talk and discussion. So thank you.